So we have mentioned that in the relational algebra, all the operands we have are relations or variables which represent relations. Relation is the only operand we have in the relational algebra. And all the operators we work on the relations and also generate new relations. And the operators are designed to do some common things, which are common queries, which we need to deal with relations in our database systems. So in other words, for the operators to be introduced in this section, relations will be their input and new relations will be their output. Okay, and this relational algebra can serve as a query, a language for all the relations in a theoretical perspective. And what are other relations we can use in the relational algebra? We cover 5 basic relational algebra operations. So the first one is a basic set operation. It covers both union and difference. The other 2 basic operators we can use union and difference. We don't have the intersection or the complement as a basic operator because it can be derived based on the union and the difference. Besides union and difference, we also have selection. And we also have a projection. We can represent the projection as a pi, as shown here. And we also have the product between 2 relations. We can represent them as times, right? And sometimes we also need to change the name of a relation, and we can do the renaming. When our relation have attribute values, we can rename some of the relations for us. And based on these basic operations we show here, we can derive some more complex operations, which include the intersection. With the union and the difference, we can derive intersection as well as complement. And based on selection, projection, and the product, we can also derive the joins. Joins cover the natural join, equal join, theta join, and the semi-join. And we will mention them and introduce some of them in the lectures. Okay, the first operation we will cover in the lecture is about the set operations. We have 2 different operations to be included. The first one is a union, and the second one denotes a difference. Let's talk about the union at first. So union denotes given 2 relations R1 and R2. If we do the union between them, we can represent the union as R1 union as R2. And this union will cover all the tuples in the relation 1 and the relation 2, right? And so prior to do the union, we may have some requirements. So if we want to do the union between R1 and R2, we require this R1 and R2 should have the same schema. I hope you still remember what is the schema, right? Schema denotes all the attributes, both the name as well as the value types. It will be the same in both R1 and R2. These 2 relations can have different names, however, all the attributes inside them, they will have the same value, the same type, as well as the same physical meanings. So as a reminder, for the union, the input will be 2 relations, right? They have the same schema. And the output will also be a relation. And the output of this union operator, it will also be a relation with the same schema as R1 and R2, right? So the output has the same schema as well as R1 and R2. We can provide you with an example. Now, given the active employees, the union, or the retired employees, then they will cover all the employees in a complaint, right? And for the union, we have an interesting part because it is a set operator. And if we have 2 relations, R1 and R2, they have some duplicated records in R1 and R2. After we do the union, how can we handle these duplicated records? What does this mean? I can provide you with an example, right? Let's assume we have 2 relations. We have some tables, right? We do it in a very simple way. We can just have 2 attributes. Let's assume we have 2 tables. The first one is active employees. The first attribute denotes SSN, the second one denotes name, right? Now here we'll first assume that the SSN for the first one will be at 1089, like at 9000, right? And his name is John, for example. And besides this, we also have some other persons inside them, right? Because this SSN will be the key for the table, right? And we don't have any duplicated SSN in the table. And you also have some names, right? The second one will be like Jim, third one will be Lucy, the last one will be Jack, right? These are all the active employees. Besides this table, we also have some other employees. For example, we don't say they are the retired employee. We can also have some other employee, for example, right? Have some other employees, and we may have some duplication between them. Like we can change this one to another person of 04. We can change this Mike, right? We can change this one to 06 or 5. And his name will be like Joe, right? And let's assume we want to do the union between these two relations. These two tables. What will be the result between them? We want to do the union as active employees, unions, other employees. What will be the result? The result will be another table, right? They have the same schema, right? They also have the SSN as the attribute, name as the second attribute. SSN is the key, right? And for the contents inside it, where we combine all the tuples we have, right? We have 4 other data tuples. So in this table, we have like 8 instances. However, by checking this table very carefully, we find some duplicated records, right? Now this one and this one, they are duplicated. As well as Lucy, right? They are all duplicated. I think we have learned this union in the discrete mathematics, right? For the sets. If we union two sets together, then in the results, we should have no duplication, right? Therefore, for the union operator, we will do the automatic duplication removal for us. In other words, we will only have one copy of Jamie as well as Lucy in the table. We will remove these 2 rows from the table. This will be the resulting table for the union between active employees and other employees, right? So they will do the automatic duplication removal in the operation. And we can write down them here. So here we are introducing the union between 2 relations. We have R1 unions and R2. We can give a large font for the union. Now we have 50 for the union. The input will be R1, right? R2. The output will be like here we can write another thing, right? We have R3 equals to we have R3. Here we have some important thing to keep in mind. The first one will be R1 and R2 should have the same schema, right? This is the most important thing. When we do the union between 2 relations, they should have the same schema. And we also know that R3 is the result also has the same schema. As R1 and R2, right? In addition, we also need to know that in this operator, we will do the duplication removal, right? In operator, right? This is a union operator we can use. Let's come back to the slides. The second one we will cover is the difference. So in the difference operator, so if we do the difference between 2 relations, like a given 2 relations R1 and R2, we want to calculate their difference as R1 minus R2, right? In this operator, we are getting all the data tuples which are in R1 but not in R2, right? The physical meaning denotes this for this operator. And for this operator, we also have something to keep in mind. The first one will be R1 and R2 should have the same schema. Prior we do the operator, we need to keep in mind, ask ourselves if R1 and R2 have the same schema or not. And the resulting relation, after we do the operator, the resulting relation will also have the same schema as R1, R2, right? The output is also a relation. The schema of the output will be the same as R1, R2 as well by default, right? We also have an example here that all employees minus the retired employees. We know they will be equal to all the active employees, right? And we can also use the example we showed before in these two tables, right? This is the union between them. We can delete it first, right? We know what it means already. Here we will try to do another operator. We want to calculate the active employees minus other employees. What will be the resulting table or relation we have? First of all, we know they will have the same schema, right? They will have the same schema. It will also be a table with two attributes, SSN and name. And if we do the minus of the active employee minus the other employees, it means we keep all the records of employees which only exist in this table, but doesn't exist in this table, right? Therefore, we can check row by row. The first one is John. John doesn't exist in this table, right? We can keep it. How about Jim? We know Jim also exists in this table. Therefore, we can remove it, right? We can do the cross first. Then we'll go to Lucy. Lucy also exists in this table. We can cross it as well. And we find Jack is only existing in this table, right? It doesn't exist here. Therefore, these two rows should be removed, right? And this will be the resulting table for the active employees minus the other employees, right? Okay, let me complete this table as well for you. So we have R3 equals to R1 minus R2, right? Input will be R1 and R2. Output with R3, right? We have the same requirements, so R1 and R2 should have the same schema, and R3 will also have the same schema as R1 and R2, right? For this one, we don't have any problem with duplications because if we do the minus, we do not create any duplications. So that's fine. We only have two reminders for you. And besides this, we also have some other operators we mentioned, right? For the sets. Let me add one more page. Besides the union and the difference, we can also have other operators. The first one we will need to mention here is the intersection. How can we represent it? We can write down with the operator we show here. Let's assume we have a new relation. R3 equals to R1 intersects with R2, right? I hope you know what's the physical meaning of this operator, right? It means the data tuples which exist in both R1 and R2, right? And this data tuple will be organized into relation R3. We didn't define this operation as a basic operation in our relational algebra because this operation can be derived from the union and the difference. And so of course for this one we also require R1 and R2 have the same schema, and the resulting R3 also have the same schema, right? We don't have any concerns about the duplications. We define this one as a derived operation. The main reason is because we have that R1 intersects with R2 actually equals to R1 minus R2. Right, and you can check it by yourself why this equation holds for the intersection. And you can even prove why this one can hold. I think you have learned this in the discrete mathematics, right? Because we can derive this one based on difference, therefore we define this intersection as a derived operator. I can provide you with some high-level ideas by drawing some plots, right? Let's assume we have two states. This one denotes R1. I can change another color for you. We can use a light color. We can also change the transparency now to 20 instead, right? Besides this one, we have another state. This is the R2, right? We can change the color as well. If we assume the first one is R1, right? And the second one will be R2. We want to calculate the intersection between them, which should be this overlapping area, right, between R1 and R2, the other two sets. And we can also show why this equation can hold. The intersection in this region equals to what? We can calculate this R1 minus R2 first, right? R1 minus R2 means this region, right? This unique region, right? Doesn't contain this overlap. And if we further use this R1 minus this region, it equals to what? It equals to this region, right? So therefore, we can also use this plot to show why this equation can hold. But you can also check back your discrete mathematics to prove why this equation can hold by yourself. Besides the intersection, we also have the complement, which is another derived operation we can define based on the union and difference. What does this mean? Given a relation like R1, right, we can calculate its complement as what? We can denote its complement as R1C. This C will be a superscript. The R1C, right? This denotes what? Generally, when we're talking about the sets, when we talk about sets, we need to have a domain, right? For domain of the sets. For example, let's say we have a domain like this. And I can change the color for it. And if we define a set R1 as shown here, I can also change the color for it. If we ever have a set R1, and its complement denotes, except this R1, the remaining elements we denote it's a complement, right? This region denotes its complement. Therefore, we know that the complement of this relation actually equals to what? Let me recover this to a normal case. It equals to the domain minus R1, right? The D denotes a complete set, the domain. I mean the read area covering R1, right? And we can just do the difference between the domain minus R1. We can derive this complement of this R1 set, right? Therefore, this complement, this operator can also be derived based on the difference operator we showed before. Therefore, we define it as a derived operator instead of a basic operator in the relational algebra. Okay, so this is the two derived operator. We will not add them to this table. In here, we just cover the basic operators. Okay, let's come back to the slides. So we have introduced the basic operators for the set operations. It covers union, difference. We also introduce why they can derive the intersection as well as the complement. Okay, in the next class, we will go through the other basic operations we can use in defining the relational algebra. So that's it for this week's class, and I hope you have a nice weekend.